Yeah, so in the last class, we learned about a phenomena called mode conversion, due to which a part of the longitudinal wave can convert to shear waves or transverse waves when there is a small incident angle across an interface between two medium. Okay. And due to that, as we saw, there will be two different types of waves going into the sample, and that can create a confusion during the test. Okay. So, it is necessary that you exclude the longitudinal part and make sure that only shear waves go into the sample. So, that there will be only one type of wave going into the sample and coming back to the probe, and there will be no confusion. Okay. And we saw that primarily depends on the incident angle, which must be between the first critical angle and the second critical angle, and we have defined this first and second critical angles. So, you have to select an angle between first critical and second critical angle when you do ultrasonic testing using angle probes. Okay. And then we also saw that you need to use something called couplant in order to avoid or in order to exclude the air gap at the interface. So, this could be an oil, grease or some gel, which can be easily applied in the form of a thin layer. And then we also saw that this couplant should have certain properties, certain requirements that it must satisfy. Okay. Okay, so, a couplant is used to avoid the air gap, so that there is no attenuation before the waves enter the sample. If you want to do a couplant free test, then this electroacoustic transducer cannot be used, because in that case you have to touch it on the surface, and once you touch it on the surface, you need to ensure that at that interface there is no air gap, and you have to use a couplant. Okay. In order to do a couplant free test, you need to use a transducer which operates differently and which does not have to be in contact with the sample, like how the normal ultrasonic transducer are. So, that kind of transducer, the working principle is also different compared to normal ultrasonic transducer, and these are known as electromagnetic acoustic transducer, because as I am going to show you now, this is based upon electromagnetic induction. So, as you could see in this case, when you have a normal piezoelectric ultrasonic transducer, you need to use this couplant to avoid that air gap, and in this case you do not really have to make a contact between the transducer and the sample, because in this case the ultrasonic waves are generated through electromagnetic induction, and that is why this kind of probes are known as electromagnetic acoustic transducer. Okay. So, let us see what is the working principle of this kind of transducer and how do they work, and what is the difference between them and the normal piezoelectric transducers. Okay. So, if you remember in the previous topic, we had discussed about electromagnetic induction, where we saw that if you have a conductor carrying an alternating current, it will have an alternating magnetic field or a changing magnetic field around it. And now, if you bring another conductor close to it, due to that changing magnetic field, the current will be induced in the second conductor. So, that is the phenomena of electromagnetic induction or simply induction. Okay. So, this is what is being shown over here in this diagram. So, these are the conductors which carry an alternating current, and so this is the sample surface. So, when you bring these conductors carrying the current close to this sample surface, and if it is a conductive, if it is an electrically conductive material, then as we have seen, currents will be eddy currents will be induced on the surface. Okay. Now, if you bring another permanent magnet, if you bring another magnetic field around this, due to that magnetic field and induced current, a mechanical force will be generated, which is known as the Lorentz force, which is shown over here. Okay. So, that Lorentz force is given by this particular equation, wherein F is the force, B is the magnetic flux which is provided by this magnet, and J is the induced current density. Okay. So, due to this induced current and the presence of an external magnetic field, this force will be generated. So, this is the mechanical force which will generate the ultrasonic vibrations. So, in this case, unlike the piezoelectric units, the mechanical vibrations or the ultrasonic waves are generated in the sample itself due to the interaction of the induced current and an external magnetic field. Okay. Which is very different from the piezoelectric units, where you need a pulse generator, some electrical signal being sent to this unit and so on. So, in this case the vibrations, the waves are directly generated into the sample, and that is why you do not really need to make that contact with the sample, and therefore, you do not need any couplant in this case. Okay. So, in scenarios where you cannot use a couplant, for example, if you have a system which is operating at high temperature, then the normal couplant that you use, like this oil and grease, they cannot be used at high temperature. Okay. So, in those cases where the couplant cannot be used and you still want to do the test by ultrasonic testing, then you have to use this electromagnetic acoustic transducers or EMAT, which will operate without the need of any couplant. Okay. So, in those scenarios these EMAT transducers are quite useful. Let me also tell you how do you go about selecting a particular frequency for the test. So, it is a broad range that you have starting from 20 kilohertz onwards and going all the way to 5 megahertz and sometime 10 megahertz also. So, from this broad range of frequencies, how do you go about selecting a particular frequency for the test? So, when you want to select the frequency, then first you know what is the effect of the frequency. If you have low frequency, what is going to happen, and when you have high frequency, what is going to happen. So, for low frequency, the penetration depth is high, but the resolution is low. Okay. Resolution is nothing but ability of the probe to detect two flaws which are very close to each other. So, if you have two defects in very close proximity to each other, so then you should have two separate defect signals, and they should appear as two distinct signal on the display, and that would happen only when the resolution is good. Okay. If the resolution is not good, then these two signals coming out from two defects lying very close to each other may just merge into one and will come as a broad peak instead of two distinct separate peaks. Okay. So, in terms of the display, if you show these two features of low frequency, it has high penetration, that means the signal that comes out will have high intensity. And you will see this kind of high intensity peaks even for the higher order back wall signals. Okay. But if you have two defects lying close to each other, then this may not be able to resolve it. Okay. So, two defects which are very close to each other, the defect echo should come as two distinct peaks, but in this case this might appear like two peaks merged into one. Okay. So, this is low resolution when you have low frequency, but penetration is high. So, when penetration is high, that means the attenuation will also be lower, and as a result you will get high intensity peaks, okay, like this, but you will compromise with the resolution. And for high frequency, this is just the opposite. So, in case of high frequency, the penetration is low. So, the back wall signals which are coming out, they will be lower in intensity compared to a low frequency wave. Because in this case, due to lower penetration, the attenuation is also high, but the resolution in this case is much better. So, like in the previous case, if you have the same scenario, two or three defects lying very close to each other, then in this case you will get two distinct or three distinct echoes like this, corresponding to two or three different defects which lie close to each other. In the previous case, we have seen that they are kind of getting merged into one peak, they are kind of overlapped. Okay. But in this case, you do not see that overlap, you see three distinct peaks for three different defects, although they lie very close to each other. Okay. So, high frequency would also give you high resolution, okay, and it has low penetration, right. So, that means this also tells you that when you want to do a closed surface analysis by ultrasonic testing, then you should go for high frequency, because as I said in this case the penetration will be lower. So, your waves will be very close to the surface. And on the other hand, if you want to go much below the surface, if you want to go to higher depth kind of inspection, then you should select a lower frequency, because in that case the penetration is higher. So, it would be able to go to the depth that you are looking for. Okay. So, that is how depending on what exactly you want to do and what kind of defects you are expecting. If you have some idea beforehand, then based upon this penetration and the resolution aspects as we discussed just now, you can select either a high frequency or a low frequency transducer. So, when you talk about the defect signal or the detectability of a defect, then one parameter comes into picture which is known as signal to noise ratio. This is written as S by N, and the idea is to minimize the noise, so that the signal intensity from a defect is increased, and often a signal to noise ratio of 3:1 is needed as a minimum requirement. Okay. And this particular parameter, it depends on several factors related to probe and the material. So, let us see what are those parameters which control the signal to noise ratio. So, this can be written in terms of those parameters in this way. Okay, so, these are the parameters which control the signal to noise ratio or the detectability of a defect. So, let me define the parameters. This W is the lateral beam width, Wx and Wi at the flaw depth. Delta t is the pulse duration. This is the amplitude of the signal coming out from a flaw, which is a function of the central frequency f naught. So, this is flaw scattering amplitude. At center frequency, and FOM is nothing but this is called figure of merit, which defines the which compares a parameter with respect to another parameter and compare them. Okay. So, this FOM in this case is the figure of merit for the noise at the center frequency. Okay, so, these are the different parameters related to the probe, and you could also see these are there are other two parameters here. So, rho is the density of the sample or the medium, and v is the velocity of sound wave in the material that the sample is made of. Okay. So, these are the parameters which will control the signal to noise ratio, and then based upon this you could see what are those parameters which will increase the detectability of the flaw. For example, if you decrease the lateral beam width, okay, so that means if you have a focused beam, then the detectability of the defects or the signal to noise ratio will be more. Okay. Similarly, if you decrease delta t, that means if the pulse duration is less, which means if it is a short length or shorter pulse, then again the detectability would be better. Okay. So, if you have a shorter pulse, the detectability is better. And here you could see that it is the signal to noise ratio or the detectability is directly proportional to the size of the flaw, which is obvious. Larger the flaw, better would be its detectability. So, that also you could see how it is coming up here in this equation, and you could see that if the density of the material is higher or the velocity of sound wave in the material is higher, then the detectability goes down. Okay. So, this is how the signal to noise ratio will control the detectability of a particular flaw. Okay. And these are the parameters which control the signal to noise ratio, or in other words, these are the parameters which control the detectability of a particular flaw in ultrasonic testing. So, today we will talk about a very important aspect of ultrasonic testing, which is about calibration. If you remember, I have told this before also, that whenever the indications are indirect, like in this case, you get a defect signal, you do not get to see the defect directly. So, that means the indications for the defect and flaws are indirect, and whenever the indications are indirect, it is necessary to calibrate the instrument before you can use it. Okay. Otherwise, you may end up with results which are erroneous. So, as far as ultrasonic testing is concerned, two types of calibration you have to do. One is for the distance, and other is for the area. Why area? Because the intensity of the echo depends on the scattering area or the area of the interface or the area of the defect which is scattering it. Okay. So, therefore, the area also has to be calibrated, so that you would be able to get some idea as to how big is the defect, whether it is a big defect or it is a small defect. Okay. So, in order to do that you need to calibrate the instrument for area also. So, let us see how this calibration is done. First we will see how the distance calibration is done, and then we will go on and see how area calibration is done in this case. So, in order to do this you need to use some reference blocks, some standard blocks which will provide you some kind of artificial flaws which is already cut into them, and the location of those flaws in the block is known, and when you do the area calibration, the area of the flaw or the size of the flaw is also known. Okay. Okay, so, these are the different types of calibration block, as you could see. For example, you could use a cylinder like this, and if you take a close look, let me magnify this, let me increase the size. Okay. So, I do not know whether on the screen you could see around this area there is a small hole. Okay. So, this hole is at a distance from the top which is 50 millimeter. Okay. So, this is at a known distance as I told. So, using this you could get an echo and then see whether it is coming at that particular distance or that time corresponding to this distance. Okay. On the time base you can see that, and you would be able to see some other holes also which are made in some other distance, because you need to collect the data at different distances to come up with the calibration curve or to do the calibration. So, here again you could see around this area, okay, there is another hole. So, this hole is at 100 mm, the first one here which you saw is at 50 mm, and this hole on the same block you have another one at 100 mm. Similarly, in the third one also you could see there is one more hole which is at 150 mm. Okay. So, like this you can make this kind of artificial flaws on these reference standards or these standard blocks, and since the location and the depth of these defects are known, you can get an echo from each of these defects and then see on the display screen whether that echo is coming at the place or at the time where it is supposed to come. Okay. So, like that by collecting the data at different depths you would be able to calibrate the instrument. Then you could have this kind of blocks also. For example, if you see this one over here. Okay. So, this is having several steps like this. So, these steps have different thicknesses. So, that means this kind of block can be used for thickness calibration. In cases where you know that there is some material loss or material thinning, and if you want to inspect that kind of damage by using ultrasonic testing, then these kind of blocks are quite useful to calibrate the instrument before you do that test. Similarly, here also these blocks also have different heights or different thickness. So, this also can be used to calibrate the instrument for the distance, because then for each of these you can collect the back wall signal itself, and that can be used to calibrate the instrument for distance. Okay, so, this is the kind of blocks, the calibration blocks you have, and in the next class we will see how these calibration blocks are used to calibrate the instrument both for distance as well as for area. So, for today this is all I will have. So, I will stop here today. I will see you next time. Thank you.